congrats on making it to the last day. And many thanks to the organizers for bringing us all here together. Okay, so I'm going to talk about a very recent work that we did with David, who is now a master student in Amsterdam, and with my colleague from Polak. It's about planting orthogonal vectors. So what's the plan? My plan is that I'm going to get some random bits and use them to generate some vectors that's new to our orthogonal with the probability. And then I'm going to use some more random bits to sample two vectors that are orthogonal to each other, and embed those two orthogonal vectors in the big bag of vectors with no orthogonal pairs. And now you see those vectors, but you forget where they are. And I claim now it's hard to find them. So we want a construction so that I know where the orthogonal vectors are because I put them there, but you don't know unless you check all pairs. And we want this construction to have some nice properties. Spoiler alert, we're not going to prove that it's really hard to find them. It's going to be a conjecture, and some of those properties are making this conjecture a bit more believable, hopefully. Okay, before I go into details, you may ask what a crazy hobby you have to find things from people. So let me give you two reasons why to look at this the problems. One is that it's just like interesting practical properties, interesting things to study. The other motivation is fine-grained cryptography or cryptography in general. So something we saw in I think 2 talks already this week, some hints of this area. So let me give you my view of what fine-grained cryptography is about. So in general, cryptographers want problems that are hard, but not too hard. So they want problems that are hard, and I can easily sample instances that are hard. So not that I only know that there exists a hard instance, but I can actually sample hard instances to which I know the solution. So examples are like integer factorization. I can sample 2 big numbers, prime numbers, multiply them. So there's a composite number which I know how to factorize, but hopefully nobody else knows how to do it. Discrete logarithm is in the same, let's say, spirit. But you can also think of a KSEM or zero-K clip, where this kind of embedding or planting is very easy. You can basically take a k-1 number randomly, select k1 that sums up to 0 and embed it in independently uniformly sampled numbers. The same thing you can do with edge weight, 0 weight, edge weight is 3. And these were problems, some of the problems people studied in the film. So why we think about theory? They already have a bunch of that problem. So a big dream of cryptography would be to build some systems. Let me call them cipher for this slide. So you can think of a digital signature, you can think of public key encryption. So make a cryptographic scheme that is provably safe until under some like very well understood assumption. So for instance, a dream theorem, a dream reduction would be showing that here we have a cipher, a crypto system that if you can break it in polynomial time, then you can solve any NP-hard problem in polynomial time. That would be nice, but we don't have it. And it feels like the NP-complete problems are too hard to make it happen. So somehow for cryptography, problems are hard, but not too hard. So what we do have is that we have crypto systems such that if you break this crypto system in polynomial time, then you can solve discrete logarithm or integer factorization in polynomial time on average. On the distribution that corresponds to how we sample the encryption keys. And let me just mention as a side note, okay, we know that you can use such, that we can build such crypto systems. We are not using those crypto systems. We do use crypto systems based on discrete log, which means that if you can solve discrete log path, then you can break those systems. But those that we use do not have this theorem in the opposite direction because they are not. If you want to have this strong guarantee, it would be not so practical. And so we in practice we use systems that are kind of like heuristically hard. They are kind of connected to discrete log, but we haven't proved that they are as hard as discrete log. But it is at least in theory possible to build something that is as hard as discrete log. But then with discrete log, we have this problem that if we ever build large-scale quantum computers, then these problems won't be really hard. We have, in theory, we have polynomial time quantum algorithms that solve discrete log and integer factorization. So there is like one way to go out of this problem, the lattice-based cryptography that you heard about, I think, 2 days ago. But we may want to think, okay, let's base our cryptography on finite complexity assumptions. These are easier problems than NP-complex problems, so maybe we can use this richer structure to build some crypto. So ideally, I would like to have something like this. I give you a crypto system such that if you can break it faster than in, let's say, n to 100 times, this means that the 0-100 k-click contact trace holds. The algorithm to break the cipher gives you an algorithm to find these tricks. We are not there yet, but we haven't been trying for a long time. I think this area is at most 10 years old and not super popular. What we have is a crypto system with quadratic gap. So even though its hardness is based on 0 k-click, the gap between time an honest party needs to spend and an attacker needs to spend is not n to 100, it's n squared. But it's like a provable end-to-end guarantee that if I break the system, if I can break the system faster than n squared, then you can find 0 k-click faster. So I guess our goal would be to have more problems than k-click and k-sum on which you can try to base your crypto systems, so that maybe you can have this larger gap, because this is result, I think, from 2019 or 2020, so it's already around for 5 years and nobody came up with an idea how to increase this gap below quadratic. Sorry, above quadratic. Okay, so let's go into some details. Like quick recall about the orthogonal vectors problem. I'll give you 2 sets of 0, 1 vectors in some dimension D. We'll talk about what this dimension should be. And we're looking for 2 that are orthogonal, which means that for every coordinate, either one has 0 or the other has 0 or both. So we never have 2 ones, but a single coordinate. So you can solve it in quadratic time, assuming this is small. And you can shape a bit of this quadratic running time if the dimension is logarithmic, if it's linear in the logarithm of the number of vectors. So they're like polynomial algorithms based on polynomial method. The shape is like this 1 over log C if D is C log n. And this, I mean, the conjecture, we conjecture that it requires quadratic time for a superlogarithmic dimension, but this is implied by SET. So we may think that it's like out of the fine-grained conjectures, one of the like most solid ones. This is about worst case, but what happens in average case? So if you just draw vectors with IID random entries, with probability of 1 being p and of 0 being 1 minus p, then first of all, the interesting regime is when p is roughly, sorry, this should be slash 1 over square root c. Because if it's much larger, then for sure you don't have an orthogonal pair. If it's much smaller, then for sure you have a lot of orthogonal pairs. So the interesting regime for deciding if a fully random instance has an orthogonal pair or not is when this is like around 1 over square root c. I think that a good constant will be around 3. And in this setting, if you think about it for a while, the vectors that are likely to be orthogonal have few ones. The less ones you have, the more likely it is that you would be orthogonal with some other vector. So there is a very simple algorithm by Kane and Williams that does like something better than n squared. It's actually the same running time as for the worst case, but it's like just basically look at the small enough set of sparse vectors and look for an orthogonal pair between them. And the first improvement over this running time, which is the same as for the worst case, so the first sign that the average case might be easier was by Josh and his colleagues from Columbia. This SOSA, they improved this saving by log C. So this is like that. So this is a two orthogonal vectors problem because we have two sets. You can generalize it to k orthogonal vectors. Everything I'm going to say today makes sense for two orthogonal vectors. So you don't need to have high k for this result to be meaningful. But if you want to focus on this cryptographic motivation, then the quadratic time problem is too little. So I will present all the results in full generality for KOV. So just to make sure we understand where we are. In the KOV, I give you k sets of vectors. And I want to find a k tuple such that for every coordinate, at least one vector has 0 at this coordinate. So all ones is a forbidden thing. And in terms of worst case complexity, basically all the twos change to k. So we can solve it in n to the k time. We can shape a little bit if the dimension is logarithmic, and under SETH, n to the k is needed for even slightly super logarithmic. And I think average case was not really studied, so I'm not sure. In worst case, you can easily reduce from KOV to 2OV, basically brute force k minus 2 coordinates and then do something on the remaining two. In average case, this argument doesn't work because the distributions change. So I don't think there is any like black box reduction between average case KOV and 2OV. So probably nothing is known. Okay. So what we propose in our work is what we believe to be the planted KOV. So we will propose some distribution for which we believe it's the correct distribution to look at. You may disagree. So our model distribution, so a distribution in which has no orthogonal vectors with good probability, we'll be looking at vectors with IID p-bias entries. So everything random. And okay, now let's talk about parameters. We need to set D to be slightly super logarithmic, at least, because otherwise the problem is not n to the k part, because we have this polynomial method that even more space shapes something. Now we need P, so the probability of 1 to be at least square root of log n over D. So like D is like log n times something slightly super constant, and we want the probability to be 1 over that. For technical reasons, we'll need p. Sorry, it should be 1/2. So the probability of 1 it's at most 0.5. Okay, and so we're going to draw an instance from such a distribution. It's a no instance, and then we will plug into this instance k vectors that are orthogonal, and they have a property that if you look at any subset smaller than k of them, their marginal distribution is the same as the model distribution. So in a sense, unless you look at all of them, you have no way of saying that this is likely to be part of the solution because they look like any other k-1 vector in your instance. So this is something that if you think about a plant K-sum, this is something you get completely for free. If you just draw random numbers between 0 and m for some modulus m, and then plant by taking one number and setting it so that it complements some k-1, then any single number or any subset of any tuple of at most k-1 numbers has the same distribution as they're all independent. With 0 k clique, it's the same, is true. So the problems that were considered so far had all of these things that we try to achieve for free. But we think so KOV has a bit richer structure. But to use it, we need to find a way of planting that does not directly. Okay, so let me tell you about so I want to sample k vectors that are orthogonal. I can do it coordinate by coordinate. And for each coordinate, I want to first decide how many ones are going to be there. It has to be less than k, so the number between 0 and k-1. And after I decided how many ones I put there, since it has to be symmetric, right? So I just pick one of the k, choose the number of ones, combinations of where to put the ones. So the only real question is, what is the distribution on the number of ones if you look at a single coordinate? So this is the correct distribution. Why? Well, I don't know. I mean, we can prove that it works. It's David who came up with this distribution. The intuition that he tried to give us is it's sort of like inclusion-exclusion principle. So you look at the like binomial distribution, so the distribution consistent with the model distribution, but now you want to forbid k-1s, so you can just remove the k-1s and increase all the other probabilities slightly, but then k-1 ones tend to appear a bit too much or too little, so you need to update it by decreasing the probabilities of all the others, and you kind of go in this fashion. Like you have this -1 to k-m terms of something that for odd numbers of ones works in one direction, for even in the other. And let me mention that because of here we're doing minus, sometimes we're doing minus depending on the parity, and for that we need that the probability of 1 is smaller than the probability of 0. Okay, and for this distribution, you can prove that if you look at any k-1 out of those k vectors, then for any coordinate, the number of ones on this subset of k-1 is this. Sorry, there should be k-1 here. So exactly like the binomial distribution. So the thing that we want to have. And the proof is, sorry, yeah, that's what we want to have. And the proof of this fact is just some calculation. So I won't bother you with this proof. Okay, is this clear?
You can tell us why this is actually nested. Okay.
No, I told you. So the number of 1 is always smaller than if you put m equals k,
Oh, I see.
Then you get p to the k times 1 minus p to the k, so 0. So the probability of k1s is 0 at every coordinate.
Oh, I see.
Okay, good question.
Yeah, I have a question.
So the support of the distribution is somewhere between 0 and 10. Yes?
If you sum this probability from like L equals 0 to k minus 1,
Yeah.
we don't get 1, right? Because
We do, unless I made a typo, which I made already 3 on this slide. So
I thought just asking, do you want k minus 1 choose L instead of 15?
Here it's k minus 1, here it's k.
Okay.
Okay. So now, okay, I explained to you what the distribution is, but now, and you can sample according to this recipe, but there is an easier recipe. The idea is that since this distribution has this k minus 1 y's independence property, then it must be possible to get these vectors by first generating k minus 1 random vectors and then doing something with the last one. Because the marginal distribution of the first k minus 1 or any other k minus 1 must be the same as random. So I can just generate k minus 1 fully random PBS vectors and then figure out what should be the probability for the last vector. And this will, of course, depend on what was generated before. The last one must be correlated with the others. So basically, for each coordinate, I compute the number of ones I saw so far on this coordinate. And then this is the correct probability to look at. And you can see that if I had all the ones so far, is it easy to see? I'm not sure. But okay, it has this property that if so far I had all the ones, then at the last coordinate I won't have a one. So with probability 1 I will get 0. And I claim that this distribution is exactly the same distribution as we saw on the last slide, it's just a different way to generate it. So even though I do something special for the last vector, in the end, the marginal distribution of every subset is going to be the same. It's just a more convenient way to do it. And the proof of before is just calculate these probabilities, which is like a bit of formulas that are very instructive. Okay. So now I want to convince you that this property of k minus 1 y independence is a nice property to have. So I will show you how to an application.
Yes, so that they are indeed orthogonal.
Sorry?
The k vectors are indeed orthogonal.
Yes, because if L was k minus 1, so I mean either here you didn't have all the ones, and they are already orthogonal I mean this coordinate is already happy. Or if L equals k minus 1, then is it easy to see?
I think it's 1 minus 2p, right? Yeah. Okay, when L is k minus 1.
Shouldn't be. If this is k minus
What happens if you generate two? Will you just generate a random vector and then the other one be like the integer complement vector? And what happens if you want to generate two?
Sorry?
If you want to generate two vectors.
Okay, when I have two vectors, then
one of them is random. What happens to the other?
Okay, good question. I think I never asked myself what happens in the special case of k equals 2. Uh, Okay, I'm sorry, I can't do this math in my head. It's too early in the day. We can talk about it offline, I guess. But what the way it should behave is that if you had all the ones here so far, then here we're going to have 0. But this is like not the only case, because if it was the only case, then it would be asymmetric. So it sometimes kind of depends on parity. Right? You have here something negative that with so this probability of one kind of depends on the parity of the ones so far. Okay. So let me move to the application. So a place where it's useful is it allows us to show a search to decision reduction. So by decision problem, I mean that I give you an instance and I promise you that it's either the instance from my planted distribution or I skip the last step of planting and it's the model distribution, and your goal is to distinguish which of the two it is. And of course, the algorithm is going to work with some success probability, like you cannot guarantee. I mean, there is a non-zero probability of drawing the same instance from both distributions, so there must be some error pair. And then the search algorithm is guaranteed to get an instance from the planted distribution, but its goal is not to add the indices of the planted vector. So, of course, the search problem is a priori harder, but the search to decision reduction shows that not really, or only up to some small factors, because I can turn a decision algorithm into a search algorithm. So something that for worst case OV is like a super standard exercise, but under this distribution, it's not that obvious. So formally, the theorem that we prove is that if I have a decision algorithm that runs in some time t of n and has let's say failure probability p of n, then I get a logarithmic increase in the running time and the logarithmic k is a constant k times log n increase in the failure probability. And the way it works is actually very simple. It's based on actually one observation. The observation is that I take the instance that you gave me, which is a planted instance, and then for some set of vectors, I discard them, and instead I put a completely random vector, so like vectors with IID p by S entries. And if the set that I replace is disjoint from the solution, then the solution is still there. So I just replace some random vectors with some other random vectors, so it's still the same distribution. So the decision algorithm should say plant. On the other hand, if I pick at least one vector from the solution to replace, so I replace some non-empty set of solution vectors and some other vector, then the remaining vector from the solution, their marginal distribution is the same as the model distribution. So now the whole instance becomes just an instance from the model distribution. So the decision algorithm should say model. So I can use a decision algorithm to answer a question whether a solution intersects in a non-empty way this set of vectors, and I can choose the set of vectors however I want. So basically, the reduction is to do the binary searches in this idea. So let's say I can do it a set by set. So first, I take my first set, I replace the first half of the vectors with random vectors. I ask my decision algorithm, is it a model or planted? And this way I learn if the single solution vector in this set was in the first half or in the second half. And then I prepare some. I mean, I do not want to necessarily decrease the instance size. So I do not because then like all the parameters change, right? I mean the probabilities and the dimension depend on the instance type. So I should not call my algorithm on a sub-instance of what I have, because then it would be a different distribution. I should always keep all the vectors or the number of vectors constant. But now that I know that this half of vectors are just random vectors, I can kind of forget about them and just focus on finding the solution in the upper. And after I do it for the first column, I do it in the second column, second set, and so on. So in total, I do like k log n calls the decision algorithm. And so this is where the running time increase comes from. But I also need to account on the possibility of errors. So basically, we do a union bound here. So our algorithm is correct if all the calls to the decision algorithm return the correct answer. So you can basically multiply the failure probability by k log n and get a failure probability of your algorithm. So this search to decision reaction makes sense if your failure probability is very small. Let's say, I mean, it has to be smaller than 1 over log n, but it's probably, so it's, let's say 1 over poly log n, or maybe some 1 over n. But we also have something for the case where the failure probability is constant. So we have a different search to decision reduction. And it's actually an adapted version of a search to decision reduction for KSUM that was published a year ago. So basically, you can show that, like, if you want a search algorithm with some constant success probability, then the other way around. Anyway, for every constant success probability, there is some other constant success probability that if I give you a decision algorithm with this probability, then I give it then I can get a search with the probability I wanted. So we show that the same can be done for KOV under our distributions. And I think it's a cool idea. It's not our idea. So the idea is the following. I keep for each vector a counter, initially they're all zeros, and then a sufficient number of times, which is order of log n, I replace some random fraction. It does, you can replace half of them, but then the convergence will be slower. So I just so it's better to pick this fraction, but doesn't really matter. I take some random set of vectors and replace with freshly sampled one. So then and run the decision algorithm on the resulting input. So the signal that I get is whether my k hidden vectors were among this random set. So if the decision algorithm says yes, then the vectors that are not replaced, so that I kept from the original instance, they're all kind of a bit more likely to be part of the solution. So I increase counters for them. I do sufficiently many iterations, and I just pick the k vectors which have highest counter. And it's not an easy calculation, but it's still just a calculation to show some concentration bounds to prove that this actually works. Yeah.
Does this reduction also explain the fact that you have k-1 bias dependence?
Yes, I mean, it's the same. The key idea is the same as in the binary search reduction. That if I hit with my replace the solution, then I get model. If I don't hit, I get random.
And it only exploits that property.
It only, yes. So this previous paper, Agrawal et al., they did it for KSUM explicitly, but it really the only property they use is that you can efficiently resample and that you have this k-1 independence. So we kind of reproved it for our system.
What happens if k is say n-1, that's one check. So
In k is constant.
K constant.
K is constant.
Okay.
Okay. So just to summarize, we gave a method for sampling k vectors that are orthogonal, but then a smaller subset of them looks completely random. And we conjecture that it still requires n to the k time to find those vectors, so that this distribution is as hard as the worst case, at least up to subpolynomial factor. And this is really just the beginning. So there's a ton of open problems or natural questions that you may have. Let me list some. So first, like the motivation for doing this is to make a asymmetric fine-grained crypto with a bigger than quadratic gap to get more problems to work with. So we haven't succeeded at this, and it's a great question for you. Then there are some natural things that you could try to do with average case problems that we so far cannot do. One is hardness amplification, which means showing that if I have an algorithm that succeeds with only small probability, then I have an algorithm that succeeds with a high probability. You can do this for k-sum by just adding another k-sum solution, like increasing its number according to a k-sum solution. So this like shuffles the instances a lot, but preserves the being it yes or no. And then again, based on concentration bounds, you can do that. But the KRV does not have this algebraic structure, so it's a priori not clear how to do such a thing. Another great thing would be to have a formal proof that on the worst case it's as hard as on the hardness of the worst case in the average case is the same, so the worst case to average case reduction. This we also don't have. This we also don't have for k-sum, so this might be a much more harder problem. And perhaps the easiest problem to work on this would be to refute our conjecture, because really it has nobody has thought about it before, right? So maybe this distribution is really easy. Maybe just you can tweak the polynomial method a little bit to, well, a little bit doesn't work, we tried, but maybe you can, a medium-sized bit tweak the polynomial method maybe could refute our conjecture, which would be really happy also to learn. Thank you very much.